Welcome back to the deep dive. Today we are tackling a problem that I think a lot of people just assume was solved like 20 years ago.
Oh, for sure.
You type a question into ChatGPT or Google and, well, it gives you an answer. It feels like the machine understands you, but does it?
I mean, that really is the trillion-dollar question, isn't it?
It is.
And that gap,
Okay.
the gap between just predicting the next word and actually understanding the story,
Yeah.
that's exactly what we're diving into today. It's called semantic role labeling.
Okay, which I have to say sounds incredibly dry. Like something a librarian does in a basement somewhere.
It does have a bit of a branding problem, but think of it this way. SRL is the difference between a computer knowing that the sun melted the ice cream and the ice cream melted used different grammar,
Right.
and knowing that in both cases, the ice cream is the victim of a delicious, melty tragedy.
Right, because syntactically, and our listeners get this, those sentences are completely different. The sun is the subject in one, the ice cream is the subject in the other.
But the event is identical. The event is identical.
Exactly. And for a very long time, computers were just stuck on the syntax, totally obsessed with the grammatical subject. But if you want to build an AI that can answer a real question, like, hey, what happened to the ice cream? You can't just rely on grammar.
You need the roles.
You need the roles. Who is the doer?
Yeah.
Who is the undergoer? Who did what, to whom, where, when, and, how?
So our mission today is to unpack how we teach a pile of silicon to stop looking at word order and start looking for meaning. And from the reading, it seems like this has been a 50-year-long argument.
Oh, absolutely. A huge argument between linguists who want this perfect, beautiful philosophy and engineers who are just trying to get something to work.
That is a perfect summary of it. The messy middle of linguistics.
It is. You have the theory, which is beautiful and, frankly, impossible. And then you have the engineering, which is messy but functional.
Okay, so let's start with the beautiful and impossible. We're going back to 1968, Charles Fillmore. Right, so in 1968, Fillmore publishes this really seminal work on what he called case grammar. And he's the one who says, stop looking at the surface.
The surface grammar is just a distraction.
It's a total distraction. He proposed that every verb has this deep structure, a set of relationships that are always constant, no matter how you phrase the sentence.
And this is where we get those classic roles we all learned about: agent, objective, dative.
Yes, so take the verb break. John broke the window. John is the agent, the breaker. The window is the objective, the thing that gets broken.
Okay.
Now, if I say the window broke, the syntax changes completely. But in Fillmore's world, the case is the same. The window is still the objective.
That seems pretty solid. It's logical. So
Yeah.
why didn't we just code that into a mainframe in 1970 and solve AI?
Because human language is just a nightmare of ambiguity. As soon as you try to pin down these definitions, they slip away. You mentioned the agent. It seems so simple. The agent is the doer.
Right, the person doing the action.
Okay. But what really makes someone a doer, this is what Cruz pointed out in 1973, the agent problem. To be an agent, do you have to have free will?
I would assume so.
Okay, so if I say, the storm destroyed the house, is the storm an agent?
I mean, it did the destroying, but it didn't, wake up and decide to destroy the house. It's just wind. It's a force of nature.
Precisely. It's not volitional. So is it an agent? Or is it an instrument? Maybe a force? Linguists literally spend a decade fighting over this.
And I can see how that just stops a coding project cold. You can't program a rule if you can't even agree on the definition.
That paralysis is exactly what led to this major shift in the 90s with a researcher named Dowdy. He looked at this whole mess and said, we're doing this all wrong. We're looking for these perfect binary categories, agent. Yes or no. But language is a spectrum.
This is the proto-role idea, right? This part actually clicked for me. It's based on prototype theory.
Yes. Instead of a rigid definition, Dowdy said we should look for proto-agents and proto-patients. He gave us a checklist. A proto-agent usually has qualities like volition, so they want to do it, sentience, they're aware they're doing it, or causation, they caused the change.
And this is the key part, you don't need all of them.
No, that is the brilliance of it. It's a weighted system. So in Storm Destroyed the House, the storm isn't sentient, it isn't volitional, but it is the causer.
So it has enough agent-like properties to win the role.
It wins the role of proto-agent.
It's like an audition. The sun isn't the perfect agent, but it's the best actor we have for the role in this sentence.
That is a great way to put it. And the proto-patient is the same. It's just the thing undergoing a change of state. And this flexibility, this was the key. It let us stop arguing about philosophy and start building data sets.
Which brings us to, I guess, the blue-collar phase of this whole field, the databases. We moved from theory to just tagging massive amounts of text. And the biggest one is PropBank.
PropBank is the absolute workhorse. It is the foundation of almost every modern system. And the reason it succeeded where others got bogged down is that the creators of PropBank basically said, you know what? We don't care about the philosophy anymore. We're just going to label the data.
And they gave up on words like agent and recipient entirely, didn't they?
Completely. They realized that linguists would never agree on whether the person getting a gift is a beneficiary or a goal. So they just replaced the words with numbers. Arg1, arg2.
That feels a little bit like a surrender, like we can't name it, so let's just number it.
It was a surrender, but a very strategic one. It turned a philosophical problem into an accounting problem. Arg0 is usually the proto-agent. Arg1 is usually the proto-patient.
But they're decoupled.
By using numbers, they decouple the label from all that semantic baggage.
So in, say, the company sold the stock, company is Arg0, stock is Arg1, simple. But what about all the extra details, like the company sold the stock yesterday?
Those are the RGMs, the argument modifiers. These are the universal tags that can apply to any verb. RGM TMP for time, RGM LOC for location. It's a very pragmatic system. It's not poetry, it's data entry.
Okay, but then we have FrameNet. And reading about FrameNet, it feels like the complete opposite of PropBank. PropBank is the accountant. FrameNet is the storyteller.
That is a very, very fair distinction. FrameNet goes back to Fillmore's later work, and it says, numbers aren't enough. You can't understand a word like buy or sell in isolation. You have to understand the whole commercial transaction frame.
The example in the notes was about blanch, like cooking spinach.
Right. The sentence was, blanch the spinach in boiling water. If you run that through PropBank, you get your spinach is arg1, water is arg2. It identifies the parts.
But it doesn't tell you much about the actual relationship.
Yeah.
It's functional, but it's flat.
Exactly. Now, run that same sentence through FrameNet. It triggered the apply heat frame, and suddenly the system knows that spinach is the food. The water is the heating medium, and the implied you is the cook.
Okay, that seems infinitely more useful if you're building, say, a cooking robot.
It is, but it's also much, much harder to scale. PropBank has these generic labels that work for everything. FrameNet has specific labels for every single scenario. A judging frame needs a defendant and a verdict.
A medical frame needs a patient and a doctor.
Right. It's incredibly rich, but it's incredibly expensive to build.
So we've got the data, we've got these huge training sets. Now let's talk about the machine itself. Section 3 in the sources covers the pipeline. How does the computer actually, how does it figure this out?
It is incredibly tricky. The pipeline usually has a few steps. First, there's parsing, just mapping the grammar. But the real bottleneck, the hardest part, is step 2, argument identification.
And is that just finding the right words?
It's finding the boundaries. We call it the null versus non-null problem. Imagine a sentence is a long string of beads. The computer has to look at every single bead and every group of beads and decide, is this part of the story or is it just noise?
So in the quick brown fox jumped, it has to know that the quick brown fox is one whole chunk, not just fox or brown fox.
Exactly. And getting those boundaries wrong is the single most common error. If you clip the argument too short, you lose meaning. If you make it too long, you include irrelevant information. It's a huge problem.
So once it finds the chunk, then it has to label it. And the notes say it uses features from the parse tree. One of them was the path. And I'll be honest, the description path from verb to node was a bit abstract for me.
Okay, let's visualize it. Think of a corporate org chart. The verb is the CEO right at the top. The other words are all employees down below.
Okay, I'm with you. The verb is the boss.
Right. The path is just the route you take on that chart. To get from the CEO, the verb, down to an intern, a noun, you might go down to the VP, then over to the director, and then down to the manager. That specific route, down over down, tells the computer exactly what the relationship is.
So a really short path probably means a close relationship, like a subject. But a long winding path means it's maybe a prepositional phrase just hang off the end of the sentence.
That's it, exactly. It's just counting the hops in the grammatical structure. And that path feature was, for a very long time, the single most important clue for these systems.
Was. I hear a past tense there.
Well, yeah, this is the modern shift. As of, say, 2021, with deep learning and transformers, so things like BERT and GPT, we're moving away from explicitly telling the computer to look at the path.
We're just throwing the raw text at the neural net and saying, you figure it out.
Pretty much. These huge models learn what we call latent structures. They don't need us to hand draw the org chart anymore. They infer the relationships just by seeing billions of examples. They've developed an intuition for the path without us ever programming it in.
Which is great for performance, I assume, but it kind of makes the black box even blacker. We don't really know how it knows anymore.
That is the trade-off, 100%. We gain accuracy, but we lose explainability.
Okay, let's pivot to something that kind of breaks my brain a little bit. Cross-lingual SRL. We spent this whole time talking about English grammar, subject, verb, object, but the world speaks thousands of languages and they don't all follow our rules.
Nope.
The notes bring up Chinese.
Chinese is a fascinating case study because it shows exactly where these English-centric models just fall apart. On the surface, it looks similar, subject, verb, object, but the details are wild.
The one that stood out to me was the compound verb issue. The example was lifa.
Right, lifa. It translates to cut hair. But structurally, it's the verb-object compound. The word for hair is literally glued inside the verb itself.
So if I say, I'm going to cut hair, in Chinese, I just say, I lifas.
Yes. And here's the problem for the AI. An English-trained system sees a verb, cut, and it immediately starts looking for the arg when the thing being cut. It scans the rest of the sentence for hair.
But hair is already inside the verb. It's not there to be found.
Exactly. The arg1 is incorporated. So the system either returns an error or grabs the wrong word because it's looking for something that just isn't there. It's like looking for your keys when they're already in your pocket.
And then there's the BA construction, which sounds like it flips the whole sentence structure on its head.
The BA construction is notorious for this. In English, we usually go agent, verb, patient. John broke the vase. In Chinese, using BA, you'd say something like, John BA the vase broke.
So the patient, the vase, comes before the verb.
Right. And if you use BEI, which is the passive marker, it flips again. If you just rely on word order, the first noun is always the doer, you will be wrong half the time in Chinese. The system has to learn that these tiny little markers, BA and BEI, completely reverse the logic of the sentence.
So if we want to build SRL for every language, do we have to hire teams of linguists to build a prop bank for Swedish and another for Urdu and one for Swahili? I mean, that sounds like it would take 100 years.
It would. It absolutely would. And that's why we don't do it. We use a shortcut called projection.
This sounded like magic when I read it in the notes. How does it work?
It relies on this idea of a parallel Bible. We have these massive amounts of text that have been translated into hundreds of languages, like the actual Bible, or UN proceedings, or even movie subtitles.
Okay, so we have the exact same sentence in English and say Swedish.
Right. We take our high-quality English SRL system and we run it on the English sentence. We tag the arg arrow, the verb, the arg1. Then we use statistical models to see which English words align with which Swedish words.
We basically map them one-to-one.
And then we just project the tags across. If sun is the arg arrow in English, we just slap the arg arrow tag on sol, the Swedish word for sun.
Yeah.
We make a huge assumption that the meaning structure is the same, even if the grammar is totally different.
It's like using a stencil. You cut the pattern out in English, and then you just spray paint it onto the Swedish sentence.
That's a perfect analogy. And it works surprisingly well. I mean, it's not perfect. Translations can be poetic or change the structure, but it gets you, say, 80% of the way there without hiring a single Swedish linguist.
So it effectively lets us colonize the grammar of other languages with English logic, which is, I mean, it's efficient, but maybe a little reductionist.
Oh, it is deeply reductionist.
Right.
It assumes all languages carve up reality in the same basic way. But for the purpose of getting an AI to understand basic events, it's a total game changer.
Wow. So we've gone from Fillmore fighting about deep cases in the 60s to PropBank acting as the accountant to neural nets just projecting meaning across languages. What's the final frontier here? The notes end on this concept of implicit arguments.
This is really the so what for the future of AI. Everything we've talked about so far assumes the words are actually present in the sentence. But human communication is just full of holes.
Like the spinach example from earlier. Blanch the spinach.
Right. Blanch the spinach. Who is doing the blanching?
Well, I am. Or you are. The you is implied.
But it's not written down. Yeah. So an SRL system looking for an object, a doer, will find nothing. It returns a null value.
And that's a huge problem if the computer is trying to track who is doing what over a long conversation.
Exactly. Or take a sentence like, the price dropped. Okay. Dropped from what to what? A human fills that in instantly. Oh, it dropped from whatever the price was yesterday. A machine just sees a void.
It completely misses the source and the goal arguments.
The next generation of this technology isn't just about labeling what's there. It's about, well, hallucinating accurately what isn't there. It's about reading between the lines to find those implicit arguments.
That feels like the real jump from smart calculator to actual intelligence.
It is. When a machine can understand what you didn't say, that's when it truly starts to understand you.
Which is both incredibly exciting and slightly terrifying. I think I prefer my machine to be a little confused about my implicit arguments for now.
Perhaps that's safer for everyone.
We have covered a lot of ground today,
Yeah.
from melting ice cream to phantom arguments. Thank you for walking us through the architecture of meaning.
My pleasure. It was fun.
And to everyone listening, the next time you talk to your smart speaker and it totally misunderstands you, just remember, it's trying to find the path through the org chart, and you probably just left out an implicit argument. We'll see you in the next deep dive.